know that, that's very helpful. It's even so helpful that the lower bound is actually 0. So you can get a regret that does not scale with log t, but is smaller than that. So if we look at, for example, what UCB does, which does not know about the structure, it just gets the classical log t rate. And if you look at what our algorithms do, so we have several variants, depending on whether we learn on the lambda or on the arm level, but they have some initial confusion, I guess unavoidable, and then they actually plateau out like you want. Okay, so we have an additive overhead over the lower bound, but we have the right rate in front of the log t, which is 0 here. Okay, maybe some other experiment if you have a linear problem. So this again, I made up some basis functions to make this a linear problem. Then you can work out the lower bound. So now it is actually a log t shape. And well, I guess the claim is that again we have some additive overhead, but the growth on top of log t is the same as the lower bound. Right? And similarly, if you just run UCB, you don't get that. You get the unconstrained rate. Right? Okay, so what did we do? So we took the lower bound for regret problems, and it was also of this min-max flavor, local minigame thing. And we put learners for that and build our algorithms that way. Okay, and the nice thing about this is that for dealing with the structure, what in the end you need to provide is this best response oracle. So within the structure, give me the closest model that has a different best arm than mu. All right, what remains to be done? Well, a terrible amount of fine-tuning. But okay, it was already quite a hassle to get there at all. What you might wonder about is what about lower order terms that don't scale with log t? Right? It's like the same question as before, but we have this initial phase to explain where there is some additive overhead, and we would like to know how it scales, for example, with the number of arms, things like that. One very interesting possibility, for me at least, is that you can actually accelerate saddle point learning, right? And get, for example, 1 over t rate instead of 1 over square root t. So it's, it remains to be seen if that can be helpful here, right? If you integrate it inside the whole process in a very careful way, it might actually do something for you. And then we can wonder about, like, okay, we saw now 2 examples where we did this minigame trick. Can we do that more often? I looked at reinforcement learning a little bit, but I couldn't even solve the best response oracle for that. So that's a bottleneck. Right. Thank you very much. So I guess even if we don't give it any constraints, will it be index based? A priori, there's no reason for it. Yes. I think. Yeah, that might actually be. So the story is different for exploration, where you don't match it, but I think here you might. So if you match the KL to the problem and you don't go through then it's only interesting if you have some structure. But even if you do it unconstrained, so like whether it comes out to be some index space. Yes. So they are at the level of asymptotic optimality. So they go through the same as we saw before, like continuity, asymptotic. So in that sense, we are sort of doing the next step by carefully tracking all the. No, we have that's on our to-do list, but we suspect that that will actually not work very well. Asymptotics they might kick in very late. We might have the same problem. Our lower order terms might also be quite large. But okay, I'm not worried about it too much because at least if you come up with an interesting style of algorithm, it will probably go somewhere anyway, right? You can file on it, make it smarter. I wouldn't so easily know how to match this type of structure adaptation with confidence intervals, for example. Okay, let's thank Walter again for making it. And then we have